So our story begins 1.3 billion years ago in a distant galaxy where this happened. This is a simulation showing the merger of two black holes. These two black holes were each approximately 30 times the mass of the sun, a couple hundred kilometers across. They were spiraling together, radiating gravitational waves. As they lose energy in the form of gravitational waves, they move closer and closer together until finally they touch, merge, form a single black hole. It rings down to a quiescent state. And that event took place 1.3 billion years ago. The gravitational waves that were emitted from that traveled outward. And then on September 14th, last year at the LIGO sites, this is what we saw. This tiny little blip at Hanford and at Livingston, our two detectors. The normal detector noise looks something like this. So this is not a huge signal, but it's very distinctive. When you overlay the two signals with the proper time delay, you see that, in fact, they match up very well, and we had very convincing evidence for the first gravitational wave detection. I won't say very much more, as you will hear. You'll hear from Sergey and from John about this later on, and so I'm going to move on. The point of this talk is that the dawn of gravitational wave astronomy is really now. Okay, so my charge, given, this was the title I was given, Advanced LIGO at the Dawn of Gravitational Wave Astronomy. So Advanced LIGO, that means I'm supposed to tell you about the instruments that made this discovery. And because it's talking about the dawn of gravitational wave astronomy, I want to look at what comes next for those detectors. What's the future going to hold for them? So just to remind you, gravitational waves have been around since 1916. It was less than a year after he published his field equations for general relativity that Einstein found plane wave solutions to those field equations that were interpreted as gravitational waves. In a couple of papers in 1916 and then 1918, he laid those out. But in the second paper, he said, basically, they're kind of useless because they're too weak to ever be detected, and so they didn't really have any practical application. Just to remind you what gravitational waves are, they're a traveling distortion of space-time. The properties are they're a purely transverse wave that travels at the speed of light. It stretches space in one dimension and shrinks it in the other, and then half a cycle later shrinks the first dimension and stretches the second one, and it just oscillates. It's a purely transverse wave. And there are two orthogonal polarizations, a plus polarization and a minus polarization, a cross polarization. And the strength of the wave is given by this quantity h, the gravitational wave amplitude, which is defined as the change in separation of two initial points in space divided by their initial separation. So equivalent to the strain. It's actually, there is a factor of 2 in there that we sometimes get a little bit careless about. Because this is India, I wanted to throw in a slide about Chandra Sekhar. Chandra Sekhar actually made 2 very major contributions to gravitational wave science. The first one was in the 60s. He used the post-Newtonian formulation to attack the problem of radiation reaction and show that the energy lost to a source was actually carried away by the gravitational waves. He showed the balance between the energy that was carried away by the waves and what was happening to the source in terms of its energy loss. So that was one very important contribution. The second one was that he inspired Bala Iyer to shift his attention to gravitational waves, which in fact may be a more significant, in the long run, more significant contribution than the first. I'm going to add a personal reminiscence. As most of you know, Chandra Sekhar was at the University of Chicago, which is where I got my PhD. I was working in infrared astronomy at the time. Chandra Sekhar was one of the real giants in the department of astronomy there. And it turned out he was on my PhD thesis committee. okay? But he passed me anyway. But then I had this job offer in 1980 to go to Caltech and to join this project to build a gravitational wave detector. We were going to have this detector built in about 5 years, and I was going to get tenure based on our first detections in the mid-'80s. So I went to Chandra Slide to ask him his advice about whether or not I should take this job. I thought, here's a guy who really understands relativity. I didn't really understand very much at the time, don't understand that much more now. But I thought he would really have some insights for me, and I assumed he would be extremely supportive and enthusiastic and encouraging to me. I explained to him what this job offer I had was, and he pretty much said, well, there's not really much point in doing that. We know that gravitational waves exist. The theory is too beautiful for anything else to happen. So all you're going to do is confirm this thing that we all know is real. And why throw away a promising career on something like that? I didn't have the good sense to take his advice. So the first detection of gravitational waves really was with the binary pulsar. So in 1974, Hulse and Taylor discovered the binary pulsar. It's a neutron star system with an orbital period of around 8 hours. One of the pulsars is a millisecond pulsar, pulses 17 times a second. It's extremely stable. And as a result, you're able to track the radial motion of that neutron star in that orbit extraordinarily accurately. And as a result, they were able to repeat essentially most of the classical tests of general relativity, the equivalents of things like the lens-tearing effect, the time, the Shapiro delay. You could look at the advance of the perihelion of the orbit of the system there. You could reproduce everything that had been done to test general relativity, typically more accurately than it had ever been done before. And then when you do that, and correct for everything else that's going on, what you notice is that there's a small deviation in the arrival time of your pulses. And in fact, what it's showing is that they're coming a little bit too fast as that system is spiraling together. You can see that the orbit is changing, that the orbital period is changing over a period of time. And when this was tracked for a couple of decades, you get a fit to it that matches the prediction of general relativity with a precision of about 0.1%. So an extremely accurate measurement. It's really the first detection of gravitational waves. Now, some people call this an indirect detection because they didn't really actually measure the effect of the gravitational waves, but it really is the first one. It's extremely significant, and it gives us a glimpse into the kinds of systems that are going to produce strong gravitational waves for us, neutron stars and black hole binaries. So how do you detect gravitational waves with interferometry? You just set up a Michelson-type interferometer, compare the length of 2 arms. These mirrors are suspended on wires. That makes them essentially free test masses, freely falling test masses in the classical sense of general relativity, at least in that horizontal plane, and for frequencies that are well above the pendulum frequency. So these become essentially free masses. And for a LIGO detector, which has 4 kilometers long, the strongest H's that you expect are 10 to the minus 22 up to perhaps 10 to the minus 21. What that means is you need to be able to detect changes in the arm length at the level of 10 to the minus 18 meters. Okay? That's the challenge. It's 1/1000th the diameter of a proton, just to remind you how accurate that is over a 4 kilometer long baseline. One of the important things about this, and I think sometimes people forget the motivation for interferometers. People thought, well, interferometers could be more sensitive than the other kinds of detectors that people were talking about at the time, namely bar detectors. And that is true, but the real motivation was not that, it was this bandwidth. The bar detectors had typically a bandwidth of about 1 hertz. They could be made be very broadband, up to maybe 10 hertz wide bandwidth. But they were really very typically narrowband instruments. whereas the interferometers have no natural resonant frequency, and they could be made to have very broad bandwidths from, say, perhaps as low as 10 hertz up to 10 kilohertz. The low end is determined by essentially really difficult to avoid terrestrial noise sources. The high frequency end is really determined mostly by the fact that we don't expect to see sources with frequencies above about 10 kilohertz. But that bandwidth was the real motivation for most of us who got into this business in the early days. LIGO was proposed in 1989 for the construction. That was already after more than a decade of R&D that went into it. It was approved by the National Science Foundation, and we started construction in 1994. The plan was to build 2 facilities. Already at that time, we were worried about the astrophysics because we put those 2 sites as far apart within the United States as you could practically do. And the reason is we wanted to be able to use the arrival time at the 2 sites to help localize sources. So already in these very early going, we were anticipating their use in astrophysics. The 2 sites rather different. Hanford is a high desert, very sandy soil. This is a pine forest in a very swampy part of the country in Livingston. But the facilities are essentially identical both places. Originally, from the very beginning, this was conceived of as a 2-phase project. This is a figure taken from that 1989 proposal, which shows that there was a planned early detector, what we call now Initial LIGO, and a later one called Advanced LIGO that would come along after we had done some more technology development and gained some experience. So this was built into the project from the very beginning, that 2-phase project. The NSF accepted this program with the expectation that both phases would be funded, provided we delivered successfully on that initial detector. This was a huge leap of faith because you notice up here, that's the prototype sensitivity that we had at the time that proposal was submitted. We still needed to push to much lower frequencies and much greater sensitivity. It was a huge leap of faith for the NSF to fund this project at that time. And this is what the Hanford facility looks like. It's dominated by these 2 long arms. What's there? The light has to travel inside of a very good vacuum. So the big thing here is a long stainless steel tube that houses that vacuum, keeps it good. The vacuum is about 10 to the minus 9 torr. It's just on the edge of what's called ultra-high vacuums. The beam tube is 1.2 meters in diameter. It's large compared to the beam because we didn't want to risk any scattered light from the walls of the beam tube. It's covered by a concrete arch to protect it from any man-made or natural disasters. It's an expensive investment and it needs to be protected. The tube is straight to a fraction of a centimeter. It was surveyed that way using GPS, one of the first times GPS was used in large-scale surveying to set this up. So it doesn't follow the Earth's curvature, it actually is a straight line. Here's the Livingston facility. The other thing you see is these buildings. This is where all the action takes place. That's where the lasers and mirrors are. The other piece of the big infrastructure are the vacuum chambers that house the mirrors and the rooms around them that house lasers and detectors and so on. These chambers are large. They're about 15 feet tall. They've got large doors so that you can install equipment, put it in. You actually climb inside to install it. So the basic operation of a LIGO interferometer is pretty simple. We start with a Michelson configuration where you take a laser beam, split it on a beam splitter, send it down to 2 mirrors, bring it back, recombine it on the same beam splitter, and look at the signal out here. That's very sensitive to the phase of the light, and so we're looking at differences in the phase, the travel time down the 2 arms. We can make it more sensitive by adding an input mirror. This input test mass is a partially transmitting mirror. What it does is when this is on resonance, a little bit of the light leaks in, it resonates in here, the light builds up inside that cavity to more than 100 times the intensity of the light going in. And that light rattling around back and forth there picks up 100 times the phase shift that it would have gotten in that initial single bounce configuration. So we call this a Michelson interferometer with Fabry-Perot arm cavities. And then we add one more thing. It turns out that the system is most sensitive if you operate your photodetector here on the dark fringe. In other words, set the interference pattern up such that the light coming out here is near the minimum of that interference pattern. When you do that, all of the laser light that comes back from the arms is sent back towards the laser and would otherwise be wasted. So we put in a recycling mirror and essentially form a second Fabry-Perot cavity that's formed by this mirror plus the entire rest of the interferometer. That increases the amount of light on the beam splitter by about a factor of 50. So it's a power recycled Michelson interferometer with Fabry-Perot arm cavities. And each of these steps is designed to gain sensitivity, but at the potential cost of complexity, makes it a little bit harder to operate. So we started off with our initial LIGO sensitivity curve. We did a detailed analysis of all the noise sources we knew of, put together this noise budget and said, this is what we're going to try to achieve with those initial LIGO detectors. There are two kinds of noise sources here. Those that we call sensing noise, which have to do with how well we can actually measure the positions of the mirrors. So photon shot noise is one of those. The residual noise from the residual gas, which is passing through and changing the effective index of refraction that the laser beam is traveling through. Those are examples of sensing noise. There are also things that are called displacement noise that are real displacement of the mirrors, real motion of the mirrors. Seismic motion, ground motion that gets through and wiggles the positions of the mirrors. Thermal noise, there's 1/2 kT worth of energy in every mode of that system. Thermodynamics tells us that. That means there's 1/2 kT worth of energy in the pendulum mode, 1/2 kT in the internal vibrational modes of the mirrors. Most of that motion is concentrated at the resonant frequency. So most of the noise in the pendulum mode is concentrated near the pendulum frequency, but there are wings to those resonances that cause noise off resonance. And we're actually seeing the suspension thermal noise is the component of that above the resonant frequency, the wings there. For the internal test mass modes, this is the wing of the resonance curve going below the resonance of the mirrors. So we worked really hard and we got to this situation. So here's what we got with initial LIGO. We matched up this noise curve, which is compared with what was in the 1989 proposal. And you can see we actually achieved what we did. We went back to the NSF and said, see, we've done this. Now give us the money to build Advanced LIGO. And the NSF, to their credit, after a number of years, almost 20 years, came back and said, okay, you did it. We'll give you the money that we promised you 20 years ago. So the question is, what's so advanced about Advanced LIGO? Well, just about everything. Advanced LIGO takes advantage of 20 years of additional R&D development over what was originally conceived of for initial LIGO. We have active anti-seismic systems. We have much better mirrors with lower thermal noise optics, higher laser power. That was something we just largely benefited from the development of technology in the optics industry. And we have a more sensitive and flexible optical configuration. I'll give you a little bit more about that. The goal was about a factor of 10 improvement in sensitivity. Since these detectors look in all directions at the same time, they're essentially omnidirectional detectors, a factor of 10 better sensitivity means you see a factor of 10 farther away or a factor of 1,000 greater volume. And that means that one day with Advanced LIGO is better than all of the data that we took with the initial LIGO detectors by a significant amount. So Advanced LIGO, we're still not yet to the full sensitivity. This is the configuration we had for the first observational run, which began in September of 2015. We have, the laser is not operating at its full laser power. We have a 200-watt laser. We've scaled it back, turned it down so that it's putting out 25 watts of laser power, simply because it's easier to get it to deal with that laser power than it is the full laser power where you have to worry about possibly damaging optics or detectors or so on. We have something here that's called a signal recycling mirror, which is put on the output. It takes some of the signal that is coming out here towards the photodetector, sends it back into the interferometer to interact coherently with the new signal that's being generated, improves the sensitivity, and also gives you ability to tune the frequency sensitivity of the instrument. So this is the configuration we were using in September 2015 when we made the detector. Just to show you how good this was, this red curve here, this one, is the sensitivity of the two detectors, the two LIGO detectors for that 01 run. Not quite yet at the blue curve, which is the full design sensitivity, because we haven't turned up the laser power, we haven't tuned some of the things, but still significantly better than the best we'd achieved with Initial LIGO. A good factor of 3 better at high frequencies, and even much better than that at low frequencies. There is the potential for future upgrades that would gain us another factor of roughly 3. Rana will be talking about that later on in this conference. The keys to achieving that higher sensitivity were the same things that I talked about before. At high frequencies, improving the laser power pushes the noise curve down in that direction. The better mirrors that we have lower thermal noise. That takes care of the noise in this intermediate region. And the better vibration isolation that we got with Advanced LIGO pushes down the noise in this low frequency region. So all of those developments for Advanced LIGO were essential to getting this better sensitivity. Just a quick walkthrough so you can see some hardware. This is the 200-watt laser developed by the Laser Centrum in Hanover, part of the GEO project, and contributed to Advanced LIGO. These are the mirrors. These are really the crown jewel of the whole operation. This mirror is a 35-centimeter diameter mirror. It's polished to a flatness of about lambda by 1,000, so about 1 nanometer RMS surface figure on that. It's coated with a low-loss coating that's got kind of less than 1 part per million of absorption, only a few parts per million of scatter. The coating uniformity is sort of plus or minus 1 angstrom, that is plus or minus 1 atom kind of uniformity across that mirror. Incredibly beautiful optics, very expensive. A lot of work went into developing those. They're suspended via fused silica fibers. The fused silica fibers have very low loss. It creates a very high Q pendulum. That's important for pushing down the wings of the thermal noise in the suspension mode. It gives great isolation. It's actually part of a 4-stage pendulum type suspension with the first stage up here, then a second stage, third stage, and then the final stage. So the isolation you get from ground motion improves with each stage, and so we get very good isolation. That is mounted on a vibration-isolated platform that uses active sensing and feedback to compensate for the ground motion. So this is a platform that includes seismometers, geophones, that are all in a complicated servo loop to stabilize the platform from which the mirrors are suspended. So I showed you this one earlier. I just want to point out that we still have a significant room for improvement, and people are currently working. We've taken the instruments down. They're out of service right now, and they're being upgraded to try to get closer to this blue curve. When that happens, our sensitivity will go up. So this is just a sort of a sketch of the signal-to-noise ratio versus redshift for this kind of source that we saw, 30 solar mass black hole binary system. So this is the one we saw here with a signal to noise ratio of 20 to 25. This is the limit. You see that it's about half of what it could have been, and that's because that source was not in the optimum place in the sky for giving us signal to noise ratio. It was a little bit off to the side in terms of the sensitivity, but this is what we might expect. When we get to full advanced LIGO sensitivity, we'll get this blue curve. So the signal to noise ratios will go up by a factor of about 3, or alternatively, we'll be able to see a factor of 3 farther at the same signal to noise ratio. And again, these future upgrades that Ron will be talking about are on this light blue curve. What does that mean? Well, higher signal to noise ratios on the small number of nearby events means that we'll be able to do more precise tests of general relativity, more precise tests of astrophysical assumptions, be able to determine parameters much better. And the higher signal to noise ratio will also let us see farther. And I want to remind you again, the detection rate increases with the distance cubed. So this factor of 3 that we might see here in terms of additional distance would be turn into almost a factor of 30 increase in the rate. So that could be, just as a kind of a guideline of order, we might be seeing with full advanced LIGO sensitivity of order 1 of these black hole binaries per day. Okay, but we'd like to do more. As you'll hear from Sergey and John, we didn't do a very good job of determining the location of this source, and we didn't really do a great job of determining its polarization. And the reason is the following. We only had 2 detectors. We get source location by looking at the arrival time primarily at the 2 detectors. With only 2 detectors, that gives you an annulus on the sky that all have the same time delay between those 2 detectors. You can get a little bit more by looking at the amplitudes in the 2 detectors, but not a lot more. Furthermore, the 2 LIGO detectors were intentionally set up to be as closely aligned as possible. And we did that because we wanted to have confidence in our first detections. And that really has worked out well for us with this one. We got signals that look very similar in the 2 detectors because they are essentially oriented in the same way relative to the source. But it doesn't give us very good polarization information. And that comes in creating larger uncertainties in terms of the distances and some of the other parameters we get. So we'd like to have better source locations and better polarization information to do a better job. The way you do that is by adding more detectors. We have a collaboration with the Virgo project in Italy, which is building another detector, comparable sensitivity to LIGO. And with these 3 detectors, we would then be able to localize sources on the sky by comparing the arrival times in the 3 detectors. Virgo is built, the facility is built, they're installing their advanced version of the detector. It could be operational by the time LIGO comes back online again later this year. That's our hope. With LIGO and Virgo working together, we actually can get reasonably good sky locations, but this is basically a resolution problem. The accuracy with which you can determine the location of a source is lambda over d, where d is the projected distance of your set of detectors. And so we do a very good job of locating sources that are perpendicular to the triangle formed by the 3 detectors, namely up here and down here. And we do a pretty terrible job of locating sources in the plane of the 3 detectors, that big swath there. And what this means is we actually only will be able to get really good localization on a fraction of the sources that we see with the 2 LIGO and 1 Virgo detector. So that's why we'd like to expand the network. And of course, you guys all know one of the key elements in that is LIGO-India, putting a detector here in India. We also have a collaborating project, CAGRA, which is under construction in Japan. They've got a very difficult and challenging detector to put together. They're hoping to have it assembled by the end of 2018, and then they'll start to try to make it work. My guess is we won't see any high-quality data from CAGRA at least until 2020. So there's, LIGO-India, the sooner it can come online, the more impact it will have. I want to just say, what do we get from LIGO-India? Just the bottom line, this is the 2 LIGO detectors, Virgo plus LIGO-India, and as you can see, we get effectively good localization, source locations over the entire sky. I want to remind you, this is what we get without LIGO-India, what we get with LIGO-India. So it's a huge win for us. And of course, the thing that is exciting is that it was just approved. And in fact, last week, the 2 governments signed, the DAE and the NSF signed an agreement. Actually, the DST also signed. So DAE, DST here in India signed an agreement, an MOU with the National Science Foundation to make this project happen. I'm just going to leave a final thought. Of course, I've been in this business now for 35 years, and so with 35 years waiting for this day to happen, I really only have one final thought, which is, wow, this is really something. Thank you. Yes. Yeah, you'll probably actually get a better answer from Satya about this. One of the difficulties in using binary black holes to do things like look for redshifts and the fact that we can determine absolute distances because we know exactly what the wave was that was emitted is that we don't have an easy way of getting an independent measure of the redshift from a binary black hole system. You do get that potentially from a binary neutron star system or a neutron star black hole system where you could identify the afterglow of the coalescence. There are some tricks using higher order harmonics of the waveforms that potentially have that ability to get the redshift independent of of seeing the coalescence in the electromagnetic spectrum. But all of those things require much better sensitivity. And so that's the directions we'll be pushing. Always much better sensitivity and more events help us.
Use squeezed light to improve sensitivity?
Yes. So the question was, is there a plan to use squeezed light to improve the sensitivity? And the answer is definitely yes. We've got a program going on. We've demonstrated that even using one of the initial LIGO detectors that we could get improved sensitivity by using squeezed light. It was not engineered. It was the sort of experiment that you cobble together as a proof of principle thing. Now we're in the process of doing a fully engineered squeezer that would be something that you could turn on and reliably have it operate 24 hours a day. But that's still somewhat out in the future. That's one of these upgrades that Rana will be talking about, I think, when he comes back and talks about some of the future upgrades.
Any other question?
Hello. You have used mirrors on the 2 arms for multiple passes. So what about the strain in those mirrors? Does that have to be taken into account in a particular way?
Well, the 2 mirrors that we have, the input mirror and we're looking primarily at the strain of the gravitational wave between those 2 mirrors.
Test mirrors.
The test mirrors.
For multiple passes, additional mirrors are being used for making it 100 times on the 2. So what about the strain in those mirrors being used for multiple passes or at the input?
Well, the strain inside the mirror itself is so small that that's really undetectable. If I'm understanding your question, if you're actually talking about the strain in the mirror itself?
No. On the two arms, we have additional mirrors for making multiple passes.
Yes.
So the way the test mirrors, there is a strain, and that is what one is detecting, the difference. So these additional mirrors being used for multiple passes, what about the strain in their positions or orientation? Is it being taken into account in a particular way? You could answer later.
The question is, they would also be affected by the gravitational wave. So does that affect the measurement of the...
Does it affect the accuracy?
So the input test mass, I think what you're calling is the input mirror. That's the one that creates the multiple passes. There is the distance from the beam splitter to that mirror, but that's only a few meters long. And we don't gain any sensitivity from that. But
that's the common part.
right.
The two on the other two arms, here, the next.
Yes. Now,
So we have these additional mirrors on the two arms.
these mirrors.
Yeah, this and that.
Yes.
So is there any particular strain being taken, or they are too close to the beam splitter?
They're so close to the beam splitter. This is not to scale.
It's very close to this.
These are really only a few meters from the beam splitter. So
I get the.
so there.
Thank you.
The strain in between the beam splitter and these mirrors is negligible.
Yeah. Stan, I mean, you've been in the game for 35 years. When LIGO was proposed, there was some expectation of what the background noises are going to be. What are the new sources of noise in your experience that were detected? Not necessarily talking about technical sources of noise, but something new, maybe this elastic noise or whatever it is. Were there new surprises at all, or was it a smooth ride?
There were a huge number of surprises. There are not so many noise sources that weren't thought of in the early going. There's a few things that we didn't really get right, even though we thought of them. For example, the initial concept for how accurately we needed to orient the mirrors was based on an assumption that they would be exactly aligned and that any change in length of the arms would be second order for the mirror, in the angles. And therefore, the requirement that we set for the angular requirements in that initial proposal were off by several orders of magnitude. We didn't understand the specification on the mirrors. And so if you go to that 1989 proposal and read how good did we have to make the mirrors, the answer was, we said that they basically, I think, need to be about lambda by 10, but we'll order them as lambda by 20 just because it's not too much more expensive to order better mirrors. So there were a lot of things that we didn't really understand fully, the requirements and all of the places where things interacted in terms of the technical noises. But there are not very many where we said we just didn't even think of that noise source. And in fact, that's really, I think, one of the tributes to Ray Weiss. In his initial concept of this, he was the guy who really started this field. He actually had enumerated almost all of the noise sources that we ultimately had to deal with.
I have a complementary question to Satya's. So looking forward in the next few years to gain another factor of 3 in strain sensitivity, what would be the most worrying noise challenges or instrumental challenges we may face?
I think the most difficult ones are going to be thermal noise. The thermal noise in the mirrors we've struggled with for a long time, and it's not something it's not an easy noise source to fix. It's not something where easily measure the thermal noise and subtract it out in some way, or improve a servo loop and get rid of the thermal noise. For the most part, thermal noise has to be dealt with by getting better materials, or using those new materials in better ways. The ideas of using cryogenics are another way of dealing with thermal noise, but they raise a huge number of problems. So I think that the most difficult noise sources are going to be thermal noise.
So my question is that what is the sort of collection of people you have put together to, this is such a interdisciplinary, complicated endeavor that you need a whole range of experts. Could you please comment on this, please?
Yeah, we have actually quite a mixture of people. The original core for this project were people who were primarily from the precision measurement community, people who did precision spectroscopy or precision measurements of this or that. But those people don't really have typically the broader understanding to be able to do a large project, how to break a project down into all of its component pieces and ensure that all of those component pieces get done well enough to get success at the end. They maybe have an intuitive knowledge of that, but they don't have the sort of the practical project management knowledge. And so in many ways, that initial core of precision measurement people sort of got conquered by high energy physics community who came in and told us how we needed to run our projects. And I think without that sort of conquest by the high energy physics community, which for a long time had learned how to run big projects, I think it wouldn't have come about. We now have a generation of younger researchers who have sort of grown up within that community, people who've sort of done precision measurement, but done it within this larger kind of project framework, and who I think maybe probably don't even appreciate, the growing pains that that this community had in those early days. And I'm not even talking now about the fact that we've had to reach out and sort of incorporate some really high-power data analysis activities. We'll hear about that from the others. I'm just talking about the experimental group. But, we need a lot more people who are very savvy with software, can pull together a digital filter and just, like that. Those are the kinds of people that have really flourished in this. People like me, I'm one of these old dinosaurs, so I don't do anything in the lab anymore because none of the young people will let me.
Hello, sir. So how is the localization of the source done? I mean, you said that we do not have much information about the locality of the source. So how do we get that information from?
I'm actually going to hope that Sergei Klemenko will talk a little bit more about that. But really, it's primarily looking at the timing. So when did the wave hit the two detectors? And that gives you the angle that the wave is coming in compared to the baseline between them. And then you get additional information by looking at the amplitudes of the different polarization components. Our two detectors, I said, are as aligned as they can be and still be, this far apart on the Earth. But that means there are still some variability in their response to the different polarizations. And so by adding that back in, we do a little bit better than just the purely timing measurement that you would get by just comparing when did the wave hit here and then here.
Can gravity waves be used for imaging objects by any chance in the near future? That's
an interesting question. I was actually invited to give a talk at an imaging conference this summer. And that would have been I didn't accept that talk, but it would have been a challenge because, in fact, for most of the gravitational wave sources, they're going to be a single pixel on the sky. This object had just a scale of a few hundred kilometers at a distance of 400 megaparsecs. So on any conceivable scale, it's a single pixel for us. So that in that sense, trying to image these things is not easy. We have to actually extract our information in a very different way. There is one kind of imaging that one can do, which is if you imagine that left over from the early universe, there might be a background of gravitational waves, a stochastic background of gravitational waves created in the early universe from, I don't know, take your favorite thing, strings or other kinds of inflationary stuff in the early universe. Pick and choose whatever you want. That background may have non-uniformities the same way as the cosmic microwave background has non-uniformities. And so we might be able to use a network of detectors to try to look at the way the overall color of the sky, the intensity of the sky over that, for that kind of a stochastic background. Now, there's no guarantee that we'll be able to even detect that cosmic microwave background, let alone be able to try to resolve that it's brighter over here than it is over there. But that's one kind of imaging that we might eventually be able to do.
Last.
I had there was a plan to set up an observatory in an Earth's orbit, as in around the Earth, an orbit, and they set up an observatory, so there's a more greater sensitivity that way, as in there's less noise by seismic noises and all.
Yeah, the project you're thinking about is the LISA project, which is a project to launch a space-based system of satellites that measure the separation of the spacecraft via optical means by interfering laser beams. But it's really a different, it aims at a different frequency band. I mentioned that we have a kind of a low frequency limit that might be 10 hertz, or maybe you can push a little bit below, due to really difficult noise sources on the face of the Earth to deal with. And you get away from those by launching into space. But anything you do in space is a lot more expensive than things you do on the ground. And because they have to work first time, they have to be tested much more extensively, you can't go back in and fix things that don't work, and so on. So I think the rule is, if you can do something from the ground, it's probably better to do it from the ground. If you can't do it from the ground, then you go to space. So LISA really aims at a lower frequency band of objects that oscillate at a sort of 100 seconds to 10 to the 5th second kind of periods, much lower frequencies than we have. So in some sense, they're kind of like the radio waves to our optical measurements, if you will.
Let's thank Stan once again for this wonderful talk. So we come back at 11 for the next two talks.